Hi, I'm Yasar. I'm a computer science student at RWTH Aachen University, and I am a working student at X41. And I like reverse engineering, which is how I found this topic. Oh wait, yeah, sorry. Quick outline, I'll first show you my motivation and then talk about a vulnerability in a library. Then we'll look at an app that uses the library, like a chat app, and we'll have a quick overview of its protocol before investigating how the library is used to implement the protocol, and then use a SAT solver to abuse of the vulnerability before concluding. So I read some privacy blog by someone, and they mentioned some chat app with an undocumented protocol, and they had like really big security claims, and that really got me interesting because it seemed a bit over the top. If you see like this, forget end-to-end encryption, the only way to ensure that your data is truly secure is with full encryption by Ginlo. It seems like, yeah. So what are they? It's a chat app based on the SimsMe app. It's a discontinued app by the DHL group, which is the new name of the German post service. And they claim to be privacy respecting and secure. But yeah, they don't have too many users, but they're open source. But even then, the source isn't like always up to date. They're really slow to upload new versions. And then the target audience, which is also why I found it relevant, is that they claim to be like the most secure communication for any organization, and at least that's their German advertising. And they aim it at businesses and doctors' offices, like for internal and external, like patient communication, and also lawyers, which, yeah, they should be secure. So looking at the first thing with like full encryption and the only way to be truly secure, looking at Signal, they switched to SQL Cipher in 2018, and they have been doing, I guess, their own on-disk encryption before that. So it's not really, yeah, if in case you were wondering, Signal does the same. So, wait, am I always looking at the, no, okay, sorry, I got confused. My main interest here was the security of the messaging protocol and its implementation. And for that, I got the app and the iOS app and threw it into some disassembler. And the first thing, basically, for anything cryptography, usually you need to generate keys, and that's why random number generators are interesting. So I looked for the random number generator function in that binary and found some chillcat random bytes and something like there's some RT50 table and an increment table and some stuff. So let's first look at what chillcat is. It's some library written in C. It implements tons of internet protocols and algorithms and data formats available, or it has bindings for tons of programming languages and runs on all kinds of operating systems. It's like first released in 2000, and I think 2008 or so they wrote on their website they had 25,000 customers, so yeah, a few people seem to use it. And then what is RT50? It turns out that's a random number generator. I'll omit the initialization here because it's not very relevant, but to generate a new random number, all you do is XOR together two numbers from the state table. You choose them by having an integer into that, an index into that table, and the second number you get by adding 103 to that, and that is like the crucial part is that the result of that XOR is both written into that table, so becomes part of the new state, and it is returned as the random number. So essentially, as anyone who gets that output, you can just record 250 of those outputs and you clone the state. And then you can run the ran function on those 250 outputs, and you just get what the next number, the real random number generator also would generate. That's basically summarized again the same thing. Yeah, you can reconstruct the state. So then let's look at the chat app. How does its protocol work? I took the info graphics from the SimsMe app and adapted them a bit because somehow they made it worse for some reason. So you can see at the very top, there's the step 1, and you generate your RSA key, which is your identity key. It identifies you, and you use it to sign messages. And then you use, in the old version, or in SimsMe, you used your telephone number, and here in Ginlo, you can also just not give that, but you register at the server. Basically, you give it your public key so that someone else who wants to talk to you can get your public key to talk to you. And yeah, one thing they don't, somehow they also dropped, how you call it, certificate pinning, yeah. And then, so you registered, and now you want to write a message to someone. You ask the server for their public key, basically, and then in the bottom right, you can see that you then generate an AES key to encrypt messages for them. Once you encrypted the message, you encrypt the key to the public key of the recipient, so that they, and then you send the encrypted message and the encrypted AES key to the recipient, so that they can, in the next step, they will retrieve it, decrypt the AES key using their private key, and then can decrypt the message using their AES key. So how and where is used as ChillCat used for the protocol implementation? They use it to generate the RSA keys, and then the static per chat AES keys. So they, in the original SimsMe app, they generated a new AES key for each message, which is the common thing to do. In Ginlo, then they decided that they wanted to keep them static for some reason. And then it's also used for the message encryption. And how did I find that out? There's a cool library, software instrumentation framework called Frida. You can use it to hook functions at runtime, and then intercept them at the entry point or right before the return. And here, at the top, you can see it still has the SimsMe name, and in the second line, you can see that there's this ChillCat random bytes mangled name of the function I showed you in the very beginning. And then we can, in the third line, you see we attach an interceptor to it and then print a backtrace, for example. And we can also extract the R250 table of the state table of the random number generator. And then, for example, this is the backtrace. During account creation, we can see that on the stack trace, there's the random bytes function is called, which is called by rand prime in the RSA class, which is called by makeKey, and so on. So we know that, it indeed is used for the RSA key generation. Then during message encryption, I hooked a few more functions, for example, import public key, encrypt string ENC, which encrypts the string and then encodes it. But there we see that the string to encrypt is an IV and a key, and it's also a time step in there. And then in the stack trace for random bytes, we see, backtrace, that some OAEP encoding is used for the RSA pattern encrypt function. And so, I don't know, I was curious, why is there some random data used in RSA encryption? It seemed, and it turns out nowadays you use OAEP encoding, which you apply to the message before you encrypt it, because the textbook version of RSA you learn in university or so is insecure, and basically it looks like this. You don't need to understand all of it, but the essential thing is there's the seed, and it is used as an input to some mask generation generating function. And what a MGF is, it takes some input and creates arbitrarily long output. So basically a hash function with very real length output. And you just make the output as long as this data block you have at the top, which part of it is the message you want to send. And you XOR that together to create this mass data block. And what it does is, when you send the same message twice, since the seed is generated by a random number generator, the ciphertext and also the encoded message of the same message is different. So an attacker can't tell that you send the same message twice. But then during decoding, we can see that at the bottom left, you get the seed again. So what that means is, as an attacker, if you get messages from someone, you can, during decryption, you can store the seed, and then you got part of the random number generator of part of the state of the random number generator of your conversation partner. And basically you can take PyCryptodome and just insert some 3 lines to, during the decryption, just dump all those seeds in an array, and So at the time, am I always showing you wrong slides? I'm so confused. Okay. So the seed is 20 bytes, and that is 5 32-bit 32-bit integer outputs of the PRNG. And then I was like, do you just need like 50 consecutive messages to reconstruct the state? It turned out that we don't get like the outputs one after another. They do 2 encryptions, first to the sender and then to the recipient. And that's why you lose 5 messages, or you lose 5 PRNG outputs, and then you get 5 PRNG outputs, and then you lose 5 again, and so on if you receive consecutive messages. So we can't just easily clone it, and we need to find a way to basically fill these gaps. And at the time I was taking the satisfiability checking lecture, and I saw some papers and research by other people that used satisfiability checkers on like reconstructing Merge and Twister and some other insecure PRNGs. And I was talking to my professor if we can use a SAT solver for this. And well, first, what is a SAT solver? It solves given a formula, it answers the question whether there is an interpretation that can evaluate, under which you can evaluate the formula to true. So just 2 simple examples, A and not B, that is satisfiable because you can assign 1 to A and 0 to B, and then it's true. And the second one, A and not A, you can never make it true because there's no assignment to A to ever, there are some really cool usages of SAT solvers. For example, the Tamarine prover was used to, I forgot the exact wording, but they basically verified some security properties of the WireGuard protocol, or more like a symbolic version of that, but essentially WireGuard is more secure because they managed to verify it with a SAT solver. You can also use it for CTFs. Like Anger is a cool tool where you can just basically tell it where you want to go, and then it tries to find via symbolic execution and I don't know, other magic, a way to satisfy the constraints to get to whatever part of the program you want to get to, and that way you can like solve some flags. Back to how we can use it in here. So we can calculate the past and future outputs of the PRNG if we just get the state, but we only get incomplete. The state we get leaked is incomplete. There are all these gaps. And we can use the solver to plug these holes basically. Since there are these relationships between if you have like if you imagine the output as a long stream of numbers, you can just basically paint this XOR between all of them, and we do that between all the states. And then the solver basically we told the solver the structure of how all these numbers relate to each other, and then like the green ones we receive from our victim, and we also tell the solver what these are, and then it can tell us what the red ones should be. And I mean, that is the very most simple attack, but yeah. This is what the code looks like. I thought it's hopefully not too hard to understand, but essentially you just create the stream of variables and teach the solver that in the bottom was 4 lines. You can go over all of them and tell the solver that the entry at I and XOR entry at I plus 103 and it must be equal to entry at I plus 250, and you just do that across the whole table. And then you insert, this modular thing is just to make sure that we skip some of the values that we don't know and insert the ones we do know into this table, assert some equality for some of them. And then that is all the solver needs to find, fill these gaps and find a model, which is the reconstructed state for the PRNG, which we can, so the scenario is to the scenario is that, the PRNG is reinitialized when the app is loaded from disk. So every time it's like deleted from memory, like if you go to Task Manager and like swipe up, or if the operating system decides that there are too many apps open, it needs to close some, then the app is deleted from memory, and that also means that the state of the PRNG is lost, and next time the app starts, it needs to be reinitialized. But usually, nowadays people keep apps open for a long time, so maybe it's more practical that way. As an attacker, you need to be Mallory in the middle on the TLS connection, or be on the Ginlo service, or like the service of the app. Mallory in the middle could also be just get onto some corporate certificate authority and man or machine in the middle that way. You don't need to, hack the public CAs. And then you need to receive 75 or more messages from Mallory, and also put some constraints on it to have the most simple version of this problem at first, where Alice doesn't do anything that can generate more random numbers, so that we can be sure that all the random numbers generated are for the messages, and that they will have the structure of 5 lost and 5 received and so on. And then once these requirements are fulfilled, Mallory can reconstruct the PRNG state once she got all these messages, and then recover the RSA or AES keys that were created in that session. So if you signed up during that session, then she can recover your RSA key and impersonate you. And if you created any chats during that session, then she can just get the AES keys and permanently decrypt any messages you sent in those chats. And now I have to look how to get to the demo to work. I do H. Yeah, and now press, right? And then. Yeah, okay, cool. So Alice registers in the app. Sorry. Sorry. Okay, I wanted to skip a bit through this, but bit hard. Then Mallory registers too, and she starts a PCAP so that she can get all the traffic. And then Alice adds Mallory to her contact. And then, she sends like 100 messages, which I sped up a bit soon. And then Alice starts messaging Bob, or first adds them. And so message that Mallory hopefully can't read. And the easiest way I found to get to the private key of Mallory to automate all of this is to just create a backup. And then we can extract from the PCAP, we can get the bodies, and from those in turn get all the messages. From those we extract all we decrypt them, get all the seeds, and then throw them in the SAT solver, and then the SAT solver will give us some state. There it is, 250 32-bit integers. And then we can take them and throw them into some other program that we then use to brute force the key to the message that we recorded from Alice to Bob. And then we see that it's a bit hard to read, but on the third line you can see that it says, this is the message that Mallory hopefully can't read. So we recovered the AST. Thanks. Okay, cool. So this is a very contrived scenario. You need like 75 messages in succession, and Alice isn't allowed to do anything in between. It's possible to make this a bit more realistic. I don't know exactly how realistic, because you can imagine it explodes in complexity if you allow different things to happen in between. Like, for example, I hope I tried to make this more understandable this way maybe. So on the left you have a message from Alice to Mallory, where you have these 5 integers that you lose, and then you receive these 5. And then on the right, you also have another message, and you don't know what happens in between. For example, Alice messages someone, and that, I don't know, it turns, then you lose 10 integers. If she creates a chat with someone, it generates a certain amount of random numbers, or there are these other action, or I mean, also she could just do nothing in between and send like 2 messages, one after another, and you don't know what's happening. And so if you want to solve the more general problem, then one also needs to encode all these possibilities, and that is a bit more complicated, and I think but just as a general idea. But so to come to the vendor response, Chillcat, he was the one developer. I think it was him you saw in green on the right, and when I was talking about the app in the beginning. He was really responsive, even though he was on holidays, which was cool. And then once he understood that it isn't too critical, he continued his holidays and added it to the next release. And then Ginlo also released an update once the fix was out. And then coming to the lessons learned, using non-cryptographically secure random number generators seems to still be a thing people do, and something worth looking for. And then if these conditions I outlined are true, where you can get some output of it, and it's not forwards and backwards secure. How you say that? You can generate past and future outputs from one single state. Then it's especially bad, and you can abuse it like this. So make sure to use cryptographically secure random number generators, and if you don't, avoid leaking their state, I guess. But even that doesn't make it secure. The important thing is to regularly audit software. You're right if it's supposed to be secure, and also maybe have your peers review it and so on. And some tools I used was Corellium for virtual iOS devices, which was really convenient. Frida, which I mentioned, and Objection was also really nice for exploring the classes and functions the app had. And if you have any questions, please ask.
Thanks a lot for the presentation. We will have time for only one question, so we try to catch up and be ready for 1:30 this afternoon. Yeah.
So thanks for the talk. All the presentation, you spoke about iOS. Did you look at the Android part? Is it the same, or there is some difference?
In the Android app, they use the proper random number generator from the operating system. The operating system provides a secure random number generator, which you should use. iOS also has one. I forgot its name exactly, but they use it for to generate the initialization vector for AES-CBC, but not for the more important things. I don't know why.
Okay, weird, thanks.
Thanks a lot. And if you have any more questions, you can ask them directly to the speaker, of course, after the talk. So see you back at 1:30. Have a good meal.